This is the second part of the probability lecture that we started last time, and we are going to talk about the Bayes theorem. Now, this theorem is a very important theorem because, in fact, it is the theorem which is at the foundation of a different approach in statistics that we call the Bayesian approach to, for example, to evaluate probability, or Bayesian approach to do inference and so on. Now, you might ask yourself what I'm referring to. In fact, normally when you were in high school, before, when you had to evaluate probability, for example, you would evaluate probability using the frequentist approach. And this is what we have been doing so far in any case. We have been basically evaluating probability based on data on a frequentist approach. But there is another approach in evaluation of probability, which is the Bayesian approach. Now, just understand something is that we are not going to discuss this approach today as such, but we are going to discuss the theorem behind this approach in probability, which means that it is a very, very important theorem in statistics, right? Now, before we really embark on this theorem, which is a Bayes theorem, it is important that we understand something else first. We need to understand what is the total probability theorem. So let's have a look at the total probability theorem. Here we go. When we refer to the total probability theorem, what are we talking about really? So maybe before we continue, I just want to make a small recap of a few things. If you are interested in the probability of an event occurring or another event occurring, this is what you would have done. You would have used union, and then you would have applied the general law of addition of any two events. If you are interested in, let's suppose, what is the probability of having A and B. So basically, A and B would be based on the multiplication rule. You would see that I did not say probability of A times B there, but I say probability of A given B times probability of B. That's basically what it is, or probability of B given A times the probability of A. That's what it is when you are interested in AND. When you are given a condition in the probability, you would understand that the condition is the application of a conditional probability, which is probability of A intersection B over the probability of B. So in any of these cases, like if you are looking at OR, you are looking at AND, you apply this formula, you are looking at OR, you apply this formula, and you are looking at a condition, you apply this formula. Now understand something. I gave you a small example of people wearing black and not wearing black, male and female last time. So from that table, you would not even need to go and do this computation using the formula. You could easily identify this value directly from the table, which you would recall last time we discussed. And the same thing here, there was no need for us to apply these formulae. We would basically just have a look at the table and identify in a matter of seconds what the probability is. However, things are not always so straightforward where you get all these information handy, where you can just evaluate the probability by just looking at the table. No, this is why you need to know alternatives, and the alternatives are the formulae that you have here, right? The formulae that you have here. It's important that you know these formulae, especially if you don't have things in a straightforward manner, like the case that we took for wearing black and not wearing black. So you saw for each of these settings, you add a specific computation. But now you talked about A union, you talked about probability of A intersection, you talked about probability of A given, All these have been discussed, but you could also talk about the probability of a single event occurring. The probability of a single event, this is what we refer to as a marginal probability. All right. Probability of A and B is what we refer to as the joint probability. The probability of B, like on its own, or probability of A on its own, is what we would refer as a marginal probability. Now, even the evaluation of a marginal probability can be done using a formula, as you can see here. Even the evaluation of a marginal probability, like probability of A, can be evaluated like this, using a formula. And maybe what I will do is, let me just take the same example that we took last time, and then we can discuss about this. So let me just create a new slide, and then we can, or let me just write it down there. Okay. We took the example of male, female, B and not B. And I recall having used 10, 20, 5, and 15. This was our data. So you have here 50, all right? Now, I talked about, as I was just saying, probability of B and F, B and M, for example, was just looking at the table. B and M would be 10 out of 50. There was no need for me to apply the multiplication rule to do that, all right? Though if I were to do it, I would get the same solution, the multiplication rule. For the probability of B given M, for example, it's just looking at the table, you will see B given M would be out of M, which is 15, divide, that is, we divide by 15 and we count how many are wearing black among males, which is 10. So basically here, you just look at it and you get the solution. There was no need even for me to evaluate this probability using the formula. But as I said to you, things are not always straightforward. But let me just nevertheless take this example to illustrate this principle of what we call the total probability theorem. What is it about as such? The first thing that I will do is let's consider the probability of a student wearing black. From the table, the probability of a student wearing black, just at first sight, you can see that it is 3/5. So it is 30 out of 50. Okay, which is 3/5. So that is the probability of a student wearing black. We don't really need to apply any formula. You just look at it and you get the solution. But as I said, things are not always so straightforward. So we might need an alternative. And this is where we get to this alternative, which is the total probability theorem. And this is what I'm going to explain to you. And we will see whether if we apply this formula, we get the same solution that we are supposed to get, that is 3 out of 5. All right. So let's try to understand this total probability theorem now and apply it using this example down there. Okay. If I ask you to find the probability of a student wearing black, you might agree with me that the probability that a student wearing black is the same as the probability that a student is wearing black and is a male, or, which is plus, probability that a student is wearing black and is a female. If you look at what I wrote here and this, you would understand that they are equal. If I'm interested in finding the probability that a student is wearing black, one way of doing it is just to look at the probability that a student is wearing black and is a male, or the probability that a student is wearing black and is a female. This gives me the probability that a student is wearing black. Now, let's try to understand this for a moment. Let's try to understand this part here. Based on what I explained to you last time, you will see that when you have intersection, you may wish to apply what we call the multiplication rule. So what does the multiplication rule state? It states that probability of B and M is equal to the probability of B given M times M, or another way is the probability of M given B times B. But here, given that I'm interested in the probability that a student is wearing black, what I would say is that the probability that a student is wearing black can be considered to be probability that a student is wearing black given he is a male times the probability that he is a male. We are just applying the multiplication rule that I explained to you last time, plus the probability, the same thing we apply here, probability that the student is wearing black given she is a female times the probability that she is a female. So this is what we get in the end. So this same formula, probability of B, has turned out to be what you are seeing down there. All right. This is what we get. The probability that a student is wearing black is finally can be rewritten mathematically using this formula that you are seeing there. We understand that part. Okay, we are just applying the multiplication rule to get this formula. Now, let's try to see what this is equal, and then I will come to this formula here in a moment. Okay, I will come to this statement that I did. Let's try to understand that now in terms of calculation. If we look at this and we do the computation, shall we get the same thing like above 3 out of 5? Let's have a look, because I'm saying that the probability of B equal to this, all right? So if probability of B is equal to this, it is supposed to be equal to 3 out of 5. So let's have a look. If we apply that, what do we get? So what is the probability of B given M? Out of male, how many are wearing black? So we know that it is 10 out of 15. Multiply by the probability of male. How many males you've got? 15 out of 50. So here we go. And then what do? You need to add with the same thing, probability of a student wearing black given she is a female. So it is 20 out of 35. 20 wearing black given she is a female. How many female we have? 35. Multiplied by the probability of a female. How many female you've got? 35 out of 50. So if we try to understand what's going on, these two cancels out. We are given it's equal to 10 out of 50 plus 20 out of 50, which is 30, out of 50, and which is equal to 3 out of 5. So in the end, we get the same solution as above here. Now, you might ask yourself, but why did I have to do all these things? As I repeat to you, things are not always straightforward where you just look at the table and then you get the solution. You need an alternative, and this is the alternative. You have a formula as an alternative. We have been able to come up with a formula that can give us a solution in case things are not so straightforward like this here, all right, to get the solution directly. And this formula that we have just applied here, that you saw me applying, this one, is what we call the total probability theorem. Unknowingly, you have just been applying the total probability theorem. So what is the total probability theorem? I guess many of you have already got it by now, but let me still explain to you. The total probability theorem states that if you have n mutually exclusive events, this is very important. We are dealing with events that are mutually exclusive, and we are referring to them as A1 up to AN. Okay, but in our example, we do not have many A's except we have only two A's. So for us, we have A1 and A2. Our letter N is equal to 2 because we are dealing with only two events. Because if we are referring to B as B, by coincidence, they are the same notation here. All right, we have the same notation. Now, what is going to be the A that we are referring to? If you look at the formula, the A is what? The A that we are talking about is the M and the F. So A1 could represent male and A2 could represent female. So this is why I'm saying in our particular example, we are referring to only two A's. One A is for male and one A is for female. So I'm trying to explain that to you with regards to a simple example. Then you can extend this knowledge for more than two events when you have not only male, when you do not have cases like male and female, but you have cases where there are more than two events. You can still apply this formula. So when you are dealing with n mutually exclusive events, in our example, can we say that male and female are mutually exclusive? Indeed, they are. So we are already satisfying this requirement here to be able to apply the total probability theorem. So we are dealing with n mutually exclusive events whose probability sum to 1. Indeed, the probability of a male plus the probability of a female is equal to 1. Why? Because male and female are an exhaustive list of outcome. All right, an exhaustive list of outcome. I think you would recall that I used this term last time rather. So remember that when we are applying the total probability theorem, we need to ensure that the events concerned, like for our example, male and female, in this particular example, because we are evaluating the probability of B. So the A is not going to be B dash, but it's going to be M and F. So we need to ensure that these events, or if you add more, all of them are mutually exclusive and their probability sum to 1, which means that they are exhaustive, which means that you did not miss any element there. Then the probability of getting B, the probability of B is defined by what? This formula states what? Let me just clean out this mess a little bit here. All right. You saw that it is equal to 10 out of 30. I'll just erase that. So let's try to get back to this and we'll see what we wrote is that the probability of B is said to be equal to the sum of the probability of B given A, J, times the probability of AJ. So this could be rewritten as the probability of, I just rewrite it differently here, B given A1 times the probability of A1, excuse me, times the probability of A1, plus we replace J is equal to 2 now, it becomes probability of B given A2 times the probability of A2. And this goes on until n if you have more than two events. But for our particular example, as I said, we have only A1 and A2, that is only male and female, only two possibilities. So I don't need to extend this formula more here. But just for information, this formula allows for more than two events. If you could also go for B given A3 times A3 plus plus B given A4 times A4 and so on, if ever there is a question where there are more than two events. So then the probability of B given A1 times A1, we are defining A1 as M. As you would see, we get the same formula that I explained to you earlier. And obviously, if you do the computation, sorry, A is F, A2 is F. If we do the computation, you will see that you get 3 out of 5 as we already did. So this is what we refer to as the total probability theorem. So, but just ensure that these two events that we are referring here, if we are evaluating probability of B, they are mutually exclusive. If I were evaluating the probability of M, right, according to this notation here, M would be my B. And what would be the A's, A1, A2? What would be the A1 and the A2? You can answer me yourself, the A1 and the A2. If M represent B, all right, if M represent the B, the A1 and the A2 represent what? The A1, the A2 represent I repeat, if the B here represent M, if the B represent M, then the A1 and the A2 represent the B and the B dash. So be careful with notation. By coincidence, this I'm using B here and I'm using black, but that does not mean that you have to evaluate the probability of black automatically because of the word of a letter B. All right, I could evaluate probability of M. If I evaluate the probability of M according to the total probability theorem, it would have been probability of M given B times probability of B plus probability of M given B dash times probability of B dash. All right. So just for your information, the B become the A that we are referring to here. All right. The B become the A and the B here in the formula become the M. Okay. Do not get confused with notations or terms. These this it is the formula, the general formula that you need to recall, and then anything else will be based on what you get as question. You might have more than two events, you might have three, four, it depends on the question, which you will have the opportunity of doing on a Google Classroom, where there is a question later on where you will apply something related to the total probability theorem. So having explained the total probability theorem, now we can move on to the next step. We just saw that we can evaluate a marginal probability using a formula, as we saw, but we can go a little bit further now and evaluate a conditional probability a little bit differently using the Bayes theorem. All right, we are going to use the Bayes theorem now. What is this formula and what do you see here? So to be able to explain that, I need to create another slide and then we can talk about it. Just a second with you. The Bayes theorem is, as I said, a very important theorem for statisticians. Maybe before we get into this formula that many of you might think it is complicated, but before we get to that, it's not really complicated as such, but I'll explain it to you in a moment. But before we get to that, let me just explain to you, where do you apply this Bayes theorem? What is the purpose of it, for example? You might not know, but this theorem is used in many applications online. All right, this theorem is in many applications online. Maybe I'll just take a simple example to illustrate it. If, for example, I am interested in what is the probability that an email is going to be classified as a spam, given a certain word, let's suppose triple A, has been used. I don't know, I'm just taking a word at random like that. A word, what is the probability that an email with this word triple A would be classified as an spam, right? Now, one of the things that you need to understand is that we can do this evaluation based on your email database. And if we do this evaluation based on your email database, or let's suppose a certain word, let's make it another word, okay? Let's suppose the word drug has been used. Now, you can go into your email, you may go into all of your emails and identify all the words drug and see how many among all these emails where there was the word drug used, and you see how many of them were classified as spam and how many was classified as a normal email. So you will just need to count that and you will get your probability out of all the emails that you had as drug. Let's suppose 100. We see that there were 10 were classified as spam, so it is 0.1. Very simple, very easy. But again, things are not so straightforward though. Why? Because if you try to evaluate this probability directly, though you can do it, but your email platform will take a long time before recognizing whether the email should be classified as spam or not. Whenever you receive an email, if there is a word drug in there, your email will take a long time before being able to evaluate whether it should classify it as spam or should not classify it as spam. So it could do it, but it will take a lengthy and unacceptable time before processing that. So to be able to avoid this lengthy processing, instead of going into all your list of emails where the word drug has been used, we can do things a little bit differently. What do we do? Instead of evaluating probability of spam given drug, we evaluate the probability of drug given spam, of drug given spam. Just look at the difference. If you go into your email and identify all these words, you would have to go and do a lengthy search of many, many emails where the word drugs have been used. But now things are different. Instead of going like this, you go into your spam. Obviously, into your spam, you will have fewer email. And when you go into your spam, you have fewer email. You evaluate how many times the word drug has been used. It's different from what we do here. But what is the purpose of doing that? It's not the same thing. We all agree that this and this is not the same thing. They are two different things. But why would I do that? Because the Bayes theorem, this theorem, allows you to um, incorporate this probability in the evaluation of this probability. What does this mean? If you are interested in the probability of A given B, you can use probability of B given A to evaluate A given B. That is the idea behind the Bayes theorem. So by doing this, by using the Bayes theorem to evaluate the probability of an email classified as spam given drug, we can uh, we can do it by using this probability that an email is an email has used the word drug given it was classified as spam. How shall we do that? You might also say they are not equal. These are not equal, but there is a way of evaluating it in such a there is a way that when you have evaluated that, you can get this. There is a way of doing it, and this is the Bayes theorem, which I'm going to explain now. So, as I said, do not misunderstand me. This and this are not equal, but we can use this one to evaluate this one. How? This is what I'm going to explain now. So I just gave you an example of where it could be applied, but just for information, it is applied in many, many other contexts as well. Now, what is the Bayes theorem? Let's get back the the previous example that we took, and then we will refer to this formula. Okay, let's get back to the previous example that we did. I already raised it, so let me just rewrite it. So this was the example that we took. Let's try to evaluate the probability of B given M. The probability of B given M, just by looking at the table, we all know that it is equal to 10 out of 15. We've already done that. Now, this is direct evaluation of the probability using the table. But let me show you an alternative. An alternative is the probability of B given M equal to the probability of B intersection M over the probability of M. We also agree with this because this is what I explained to you in the first part. Excuse me. This is what I explained to you in the first part. So the probability of B intersection M is 10 out of 50. Remember, B intersection M is not given M, so it is basically 10 out of 50. B given M directly is 10 out of 15, but if you are evaluating B and M, there is no reduced sample space. It's the whole thing, that is 50. Divide by the probability of M. Probability of M, how many males you had? 15 out of 50. Which is equal to 10 out of 15. Same thing like above, okay? Which is 2/3. But I will show you now another way again of evaluating this probability, which is going to be based on the conditional probability. Another way, let me just show you that. If we evaluate probability of B given M, probability of B given M we can say, we have already said rather, that it is equal to the probability of B intersection M divided by the probability of M. All right, we just saw that. But let's try to apply a little bit these different concepts that we learned earlier. If I am interested in the probability of B intersection M, what is the probability of B intersection M? For your information, we learned earlier that the probability of B intersection M equal to the probability of B given M times the probability of M, or the probability of M given B times the probability of B. The question that you need to ask yourself is that in this numerator, we have two possibilities. Either I write down this one or I write down this one. The question is, which one shall I write? Shall you write the first one? If you are saying yes, you are wrong. Why? Because how can you evaluate probability of B given M where you still have B given M in there? That doesn't make sense. In the previous case, when you were evaluating probability of B, you could say probability of B given M because there is no B in there, right? When you did that, probability of B equal to the probability of B given M. Probability of B given N times probability of M plus probability of B given F. Probability of B given M is not probability of B. This is why you could do it. But here, that doesn't make any sense to use this one because you can't evaluate an unknown by itself in there in the formula. The best way is to have it by using probability of M given B times the probability of B. This is where the Bayes theorem is helpful, by the way. Probability of spam given word is equal to the probability of word given spam. Remember, probability of spam given the word that we just used earlier. Uh, I forget the word, by the way, which I used, but the word that we use, probability of B given the word that we use, is the same as the probability of the word given B times the probability of B, all right? So probability of spam given the word is equal to the probability of the word given spam times the probability of spam. Now you see how this is being used. You are not saying that the probability of B given M is equal to the probability of M given B, no. But you are saying it is equal to the probability of B given M times the probability of B, but it is going to be divided by something else. So the formula doesn't end there. So here, what we just did here is that we have applied the multiplication rule. We have applied the multiplication rule, all right? But what shall we do here? I'm sure that many of you would think about it already. For this marginal probability, if I apply the multiplication rule in the numerator, now I can apply the what rule for the denominator? I can apply the total probability theorem for the denominator. Now, the total probability theorem, you remember probability of B is equal to the probability of B given A times the probability of A, the AJs. So the probability of B now is not B but M. So it's going to be what? Probability of B is defined as M. So probability of M equal to the probability of B, which is M, given A1. What is A1 now? A1 is not F anymore, but it's going to be B and B dash. A2 is B dash. So it's going to be equal to, I write it down there, probability of M given B times the probability of B plus probability of M given, excuse me, given B dash times the probability of B dash. So what is happening here is that I'm applying the total probability theorem. I repeat, do not get confused with terminologies like B. You think that it is always B that should be here, all right? It's not that. It's just a term. B is replaced by M and A is replaced by B in our context. The formula is a general rule, the formula that we did here. B in our example is replaced by M and the A is replaced by B and B dash, all right? This is what is happening. And M given B or M given B dash, all right? So this is just for your information. So here we go. We have come up with another rule where we have applied the total probability theorem here. This is what we did in this particular case. So now let's try to evaluate this probability that we just got and see if we are going to get the same thing if we apply the conditional probability 10 out of 15, and see if we get the same thing if we had to evaluate it directly, which is the same thing here. But let's have a look if we get the same thing. So remember, in the numerator, I applied the multiplication rule, and in the denominator, I applied the total probability theorem. Now, just for your information, you would see that each time when you apply the total probability, the Bayes theorem, whatever you got in the numerator will also come back in the denominator, all right? Will also come back in the denominator. This is something that you need to realize. Now, just for information, let's suppose that it was not black and it was not this B and B dash, but let's suppose it was white, red, blue, yellow, green. Let's suppose this was the option, red, blue, yellow, green. All right. If I'm looking for the probability of a person wearing red given is a male, you would say that it is a probability that the person is a male given is wearing red. Times probability of red, you will repeat the same thing here. Plus, you do not do that. You do not do like is a male given is not wearing red times the probability of not wearing red. Do not do that. If you have more than two events, if you have red, blue, yellow, and green, you will have you can't say that the you cannot say that the blue and the yellow and the green can be encompassed into only this. This doesn't make sense. You can try it on a question, you will see that they are not equal. You would have no choice except doing it one by one. That is probability of m given blue times the probability of blue plus probability of m given yellow times the probability of yellow plus probability of m given g times probability of g. You would have no choice. You would have had to go through all of these. Do not just encompass them into this dash. For our particular example, because there are only two events, you can do that. It's okay, but it's normal. But for more than two events, don't think that all of them will be encompassed into one thing here. This is not the case. So let's evaluate the probability of b given m, m given b. So m given b out of b, which means out of 30, how many are wearing black? Say 10. Multiplied by the probability of someone wearing black is 30 out of 50. Probability of someone wearing black is 30 out of 50. This is my numerator. My denominator, as said, repeat the same thing here. Plus probability of m given b dash. So the probability that a student is a male given is not wearing black. So among those who are not wearing black, you had 20 people among them. But how many of them are wearing, how many of them are a male? So you have 5 here. Multiplied by the probability of b dash. That is how many are not wearing black. It is 20 out of 50. Let's try to evaluate that. So you have above, these two cancel out, which gives you 10 out of 50. Divide by what? 30, 30 cancels, this cancels, so you have 10 plus 5, which is 15 out of 50. So in the end, you get 10 out of 15. Here we go. Now, having said so, you see that you've got another formula. You add the conditional probability, but sometimes even the conditional probability is not sufficient to solve such types of problems. Then you use this one. What is this one? This one is what we call the Bayes theorem, right? The Bayes theorem that we just spoke of here, the Bayes theorem. So what is the Bayes theorem about? So let's just go back to the example here to illustrate what's going on, all right, in the formula. You have applied the Bayes theorem where you are dealing with only two events again. B and B dash, M and F, only two events regarding rather M and F. Okay, so let's come back here and try to understand and make an analogy between what you are seeing there on this screen and what you are seeing there. All right, let's try to make an analogy between these two things. So if B1 up to Bn, if B1 up to Bn are mutually exclusive events and exhaustive events. Let's have a look at this for a moment. If B1 up to Bn are mutually exclusive event and exhaustive event. Sounds like a repetition of something that we already just said, isn't it? It sounds like a repetition of something that we have been saying. What did we say? We said in the total probability theorem, if we have n mutually exclusive events whose probability sum to 1, just for your information, when you say probability sum to 1, it means you have a list of exhaustive events. I think I already mentioned that earlier. So you are seeing something similar. The only difference that you have in this one and the next one is just the term that is used. Here we are using A, but in the other one it is B. So I repeat, you should not be focused on the letters. The letters are just here to illustrate something. It's not the letters that matter, it's the principle and the formula form in the end, the form that matters, not the letters. I could have replaced A, B. I could have replaced this by A1, A2, and then the only difference, this would have been A and this would have been B. So, but here it doesn't matter, it's just letters that are being used. But the principle is that you are still dealing with a set of mutually exclusive events whose probabilities sum to 1, just like in the same thing like total probability theorem. In fact, it is normal that uh, these two conditions are the same. Why? Because remember that when we did this here, the denominator is the application of the total probability theorem. So the Bayes theorem in itself, it uses the total probability theorem. This is why it is quite natural that we have the same conditions that were used in the total probability theorem that is being used here as well. So there is no surprise about that. Such that the probability of the BJ's is greater than 0. Now you might ask yourself, but why do I say probability of BJ should be greater than 0? Why? I'll explain that in a moment, because let's come back to that afterward. For all value of j's, and then for any event A, of course probability of A greater than 0 again, and A is a subset of the union of BJ's. What is this about? I'm going to get to that in a moment. Then the probability of BK given A is equal to the probability of A given BK times probability of BK times, this is times, probability of BK over what you see here. Now, just notice something. You are interested in B given A. Forget the K for a moment. It is B given A. What are you using? A given B. This is where the Bayes theorem is being applied. Now, let's try to understand something. How does this apply to what I just did here? If we have a set of mutually exclusive events, and what is of interest here is the probability of BK given A. What does this mean? According to the conditional probability rule, it is equal to the you forget the K for the moment. It's just I'm writing C. It's like as if I'm writing C or I'm writing D given A, right? But it's just that we have a subscript with it. I will explain to you what the subscript is about in a moment, but for the time being, if you look at probability of BK given A, it's the same as if I'm saying probability of BK intersection A over the probability of A. This is why I said this should be greater than or 0, greater than 0, because if it is not greater than 0, if it is equal to 0 rather, this formula is undefined. If the probability of A is 0, the formula isn't defined, then there is no need for us to evaluate any Bayes theorem or whatever, because probability of A is 0 means there is no event A. This is something that is quite trivial and simple to understand. So we are just basically saying that there is a list of events that exist as such and are not is not equal to 0, which makes it's just a simple trivial thing, but it is mentioned here. So the next step is how does this is why I just wanted to show you why it is saying probability of A is greater than 0. Because if this is equal to 0, the whole thing doesn't make any sense here. Now let's try to see how this applies to our example. If we look at this formula, now there is still this part that I need to explain, and I will explain that in a moment. Now, but before I explain before I come to that, let me just extend this formula so that you can see. The other way of writing it down is A given bk. You might still ask yourself, what is this bk? All right, we'll get to that, don't worry. Is the probability of A given j is equal to 1. So b1, you place 1 here, times probability of b1 plus the denominator, it goes on probability of A given b replaced by n, the last one. Just write it down there, plus probability of A given bn times the probability of bn. This is what we have as a formula. For us, we need to understand what is our bk, and we need to understand what is our A in the example that we have been working on there. So let's try to understand this for a moment, okay? I'll just erase some of these things so that we don't get confused in the explanation. I'll just erase that as well. We say that the probability of B given M is equal to that, okay? So probability of B given M is equal to that. Now let's have a look at the Bayes theorem, all right? The Bayes theorem says the probability of BK given A. Look at that. BK given A. What is BK? It means that there is a subscript that is used there. It's one of the different possible values of K for B. B can take different possibilities. Let's suppose n different possibilities. If B can take n different possibilities, then we are referring to K as being one of them. K could have been equal to 1, K could have been equal to 2, or whatever it could have been, but it is one of all the possible B that we have. It is one of all the possible values of n that we are dealing with. So K could be any one of it. It could be 1, it could be 2, it could be 3, it could be 10, I don't know. But for our example that we just took here, how many possible values of B do we have? We are evaluating the probability of BK given A. So if we relate to our example here, the probability of BK given A is the probability of B given M. So what is A? A is M, and BK is what? BK is the person wearing black. So our K, if we define B as B1 and we define B dash as B2, then our K is equal to 1, for example. But I'm not going to write it down, but I'm just showing you the analogy to see if ever what you see in the formula here is the same thing like what you are seeing here in this part, okay? So probability of BK. BK is B, which means B1, all right? Given M is equal to what? The formula states that the probability of BK given M, so let me just write it down here rather. bk given m, bk given a, which is b given m. It's equal to probability of m given b. I'm not writing the bk here, I'm just writing the b instead of writing b1 times the probability of b over what? So in other words, this is m, this is b, this is b. Divide by what? The same thing. A, which is m given b times the probability of b plus this is the same thing. This part is the same thing. M given b times probability of b. But what about this part? This part is what? Still m given b2 because now we don't have more than 2. So in the end it is equal to the probability of a given b2 times the probability of b2 because our n for the example that I just took is only two possible value of b, that is b or not b. B1 is b, b2 is not b. So what is happening here? A is m, just follow the notation. A is m given b2. B2 is what? B2 is not wearing black times not wearing black. So this is a little bit about the notation. And we can try to see if ever what we are seeing here is the same thing like what I wrote on the slide. So let me just put that neatly here, just for you to see what I wrote. So the probability of bk, which is b given m, which is a is m, is equal to the probability according to the formula here. A is m, so m given, what is bk? Bk is b. So the formula says that this is what I need to write. Divide by probability of j is equal to 1. So probability of m given b1 times probability of b1. So based on this example, I said b1 is b. So I don't need to write down b1 here. I'm just going to write down b. So probability of m given b times the probability of b plus probability of m given b2 times probability of b2 because we have only 2. So what is b2? b2 is b dash. So I don't need to write down b2, but I just write down b dash. So m given b dash times the probability of b dash. So let's have a look now. Is what I wrote here, according to the formula that you got here, the same thing that what I explained earlier? So m given b times b over m given b times b plus m given b dash times b dash. M given b times b, m given b times b plus m given b dash times b dash. So what you saw here is an application of the Bayes theorem, of course in the simple setting, that is where there is only two events. So I explain that again here for b given a. So where you have only two events, all right? You don't have more than two. But if you have more than two, then you will need to extend that further. Instead of having a given b2, you would have to go for b3 and so on. So that is the total probability theorem. Now, the question that you need to ask yourself is, what is this? What is this? A is a subset of the BJs. Let me just explain that quickly. So I've shown to you that this formula is nothing, you have nothing to be afraid about. It's just that there are different terms that you are not used to. Like the BK is one of the B's. For me, one of the B's that I'm discussing is B actually. It's not B dash, but it is B. It could have been B dash, probability of B dash given A. So then B dash is like B2 if you want. So K would have been 2. But here I'm dealing with k is equal to 1, which is b. K is equal to 1 means it is equal to b. So what is this notation? Let me just erase all this and show you something. You see, one of the questions that you need to ask yourself is, if I ask many of you to draw a Venn diagram to represent male and female, If I ask many of you to draw a Venn diagram to represent male and female, this is what you would have drawn, isn't it? I'm sure that you are answering yes right now, but this is wrong. Why? Why is this wrong? It is wrong because of one simple principle. It is wrong because if you write it like this, you are allowing for other possibilities apart from male and female. But for the time being, what is you need to consider, it's not for the time being, but rather what you have to understand is that there are no other possibilities apart from male and female. God created us male or female, so we understand only that. So, in other words, either you are male or you're female, you cannot be anything else. If you draw it like this, you are implying, you are saying that there could be something else. But I don't buy the fact that there are not something else. So, here what is happening is that the way of drawing it is like this. The correct way of drawing this is something like that. Okay, let me just show you that. This is a correct way of drawing a Venn diagram where you have male and female. You cannot draw it like this. Like this, one thing is correct, is that they are disjoint, which means that they are mutually exclusive. You are doing it well by doing this. But there is one thing that you do not do well, is that you are not showing that they are exhaustive. All right. Male and female are exhaustive. There are no other possibilities. So if they are exhaustive, then you cannot draw it this way. The only way to draw it to ensure that it is exhaustive is by drawing it in the form of a partition. You have a partition of a Venn diagram here. So this is why you have to be careful, is that when you draw this, it should be like this. So why did I show you that? This is what? Is disjoint. This is disjoint. This is firstly disjoint because you see that M and F are separated like above. But in addition of being disjoint, they are exhaustive. Sorry, they are exhaustive. You can understand that they are exhaustive because they fill the whole sample space. Now, why did I show you that again? The question is because we are saying that if we have a set of B event, B1, B2 up to Bn for our example, there are what are the B that we are referring to? For us, our B that we are referring to is B and not B. B and not B. This is what our B was referred to. All right. For us, the B is either B and not B. Remember, B1 was somebody wearing black and B2 was somebody not wearing black. So we are saying that A should be an element of the union of BJs. A should be an element of these two. So in other words, we are saying that A, which is male, should be part of B and not B. It should be part of both. Which means basically what? Which means that, for example, male should be part of B and not B, which means that, for example, I'm not expected to get something like this, 0 here. If I'm getting something like 0 here, this creates a problem because it does not satisfy this part, which means that B is not a subset of the union. M is not a subset of the union. M is just a subset of B. So then it does not satisfy this rule. So this is why I'm saying sometimes when you look at these kind of formulae, you might be lost, but in fact they mean a lot of things. They are saying basically that you should have a number here. You cannot have 0, for example, here, which means that it creates a problem if you have 0 here. So this is why you saw this formula. I think I explained whatever had to be explained here. And the next step is now you should be able to do an activity that I'm going to give you later on. But I'll take an example first, okay? So this is done. I explained to you what is the Bayes theorem and what is the purpose of it and how this formula that you might have been afraid of translate in this example. Okay, there is an activity on Google Classroom where you won't have only 2 events, but you will have more than 2 events, and you will be expected to apply these things. I repeat, when you have more than 2 events, please do not bring all into one step, like A dash, like A given B dash. You have to do them separately. Remember that, because doing them separately is not equal to what you are seeing here. They are different. Okay, so remember that. Do them separately one by one if ever you have more than 2 events. So let's take an example to illustrate. These are just definitions that you can read afterward. Now let's take this example, and then you will do the activity 1 that I give, the activity on Google Classroom. I'm not sure if it is activity 1 rather, but it is an activity that you will see on Google Classroom where you will be having the Bayes theorem to apply. Okay, you will go through it and you would identify in any case you are going to apply to do all the activities on Google Classroom, so you will be able to know when you're applying the Bayes theorem there. Now for this part, let's read this and let's try to do this activity together. Okay, I guess some of you might have tried it based on your independent learning, but some of you might not have tried it. So let's explain that. In a courtroom trial with a male defendant, CCTV evidence from a pub shows a crime being committed by an individual. Now, just before I carry on, whenever I'm doing an activity together with you on a video recording, please just pause the activity. All right, pause it and try to do it before I start giving you the solution to it. All right, when I've given you the solution, then you can try to see whether you got the same thing or not, but do not just listen to me at one go. Like right now, just take a pause of a video and then try to do it. After you have done it, then you can listen to what I'm explaining now. Okay, this is just an advice. It's going to be like that for any other video recording that I might do and where I'm discussing an activity. So just take a pause, do it, and then you come back to what I'm saying to see if ever you are getting the same thing or not. So in a courtroom trial with a male defendant, CCTV evidence from a pub shows a crime being committed by an individual carrying a bottle. But it is unclear whether this is a male or female. Just by reading this, I'm going to do this activity together with you. Just by reading this, I get a lot of information about what's going to happen here. All right. What do I mean by that? You are getting information in terms of a person carrying a bottle. You are getting information about the fact that the person is a male. But what is unclear? What is unclear is whether the person is a male or a female. So in the end, even if I don't read till the end, I will already have an idea that there are 2 events here. A person is wearing bottle and a person being a male or female. But the interest would not be necessarily in terms of probability of B, but the interest would be mainly about the probability of M. Maybe not M, but something related to. But in the end, it will be related to the probability of finding a person whether he's a male or not male. Just by looking at that, because it is unclear whether this is a male. So this is where the probability comes in. It's not about carrying a bottle, because it's a fact that the person is carrying a bottle. But what is unclear is whether it's a male or not a male or female, the one who committed the crime. So in other words, it's a probability of the gender that I'm going to be computing. But let's continue reading to see if I am right or wrong. A witness reports seeing seeing the defendant carrying a bottle around the time of the offense. Suppose at the time of the offense there are an expected 60% of males in the pub. So you already can write down the probability of male is equal to 0.6. Now, just for information, it's always good that you define whatever events you are using. M represent male defendant. Just do it for me, please. Do not just write down probability of M without explaining it. For the sake of time, I'm just writing down probability of M and I'm explaining it to you. But in the context of an exam, you cannot expect me to understand what you are writing here as an event. Okay, if you are using A, I may misunderstand what A is. So this is why you need to define your terms, but your events. So the probability of M is equal to 0.6, but obviously probability of female is 0.4. Furthermore, an expected 2% of male and 1% of female carry battle. So let's try to translate this information. That's how you answer a question on probability. You should not answer questions like the probability, how do we say, an expected percent of male carry battle. You say male carry battle, or you write down things like that, carry battle. Do not do these kinds of things. If you do these kinds of things, it means that you are not understanding what is being asked. This is not what you should do. You should write down things in terms of sets theory that I explained to you earlier. That's how we would know if you have understood or interpreted correctly the question that is given to you. Because at times people are getting the correct solution without even getting the proper interpretation of a question. So it also happens sometimes like that. It's important that you write down properly what is given to you. Furthermore, an expected 2% of male carry a battle. What does this mean in terms of probability notation? What does this mean in terms of probability notation? What is it saying? When it says, furthermore, an expected 2% of male carry battle. So it says 2% of male carry battle. So among male, you are looking at those carrying battle, but you are not saying among those who carry battle, how many are male. No. Neither are you saying how many are males carrying a battle. There is a difference. What you are reading here is an expected 2% of male. That does not mean the 2%. Some of you are thinking about this. I think some of you are thinking about this right now. If you are thinking about that, this is wrong, because you're not talking about the whole sample space, that is, all the possible people who could have committed the crime. No. When you're saying of male, you are referring to only a particular part, a segment of the whole sample space that we were referring to. And that segment is male, so it is among male. So in other words, if it is among male, you are referring to a reduced sample space which is given male, and then you are evaluating the probability that the person is carrying a battle. So this information of 2% of male given male is carrying battle is written like this, okay, in terms of probability. You have to understand that it's very important that you write down these things properly. You get used to writing these down. If you do not write these down, you will still have misunderstanding when you interpret questions on probability. You have to force yourself to think in terms of sets notations, in terms of notations like B union M, B intersection M, etc. You have to force yourself to understand things like this. Because if you start writing down probability person is carrying battle and what uh, male carrying battle. If you write down, for example, male carrying battle like that, you might get it wrong because you might think that you are talking about probability of M and B, but this is not the case. This is why you have to force yourself to understand properly and translate that in sets notation, because the sets notation is going to help you later on to determine what formula to apply, whether to apply the multiplication rule, whether to apply the addition rule, whether to apply the conditional probability or the total probability theorem or the Bayes theorem. So the next one, I don't need to explain. I guess you would have understood that this is B given F. So what does all this mean then? Your question now is what? How strong is the evidence against the defendant? And what is going on with the defendant? We know that the defendant is a male client, but what is unclear? Whether the person who committed the crime is a male or a female. So in the end, what I'm evaluating is still the probability of M. But of course, that's not what is asking me. We are talking about the defendant who committed a crime, and by carrying an individual, we know that the person who committed the crime was carrying a bottle. So we need to evaluate the probability that this defendant, given he was carrying a bottle, what is it? If it is high, then there is strong evidence against the defendant, because we know that the defendant was carrying a bottle. So we have to take this into consideration. I can't just evaluate probability of M. That would not make any sense, because we have an information that he was carrying a bottle. So what is the probability that he is a male given he is carrying a bottle? That is, what do I mean by it? He is a male, not the defendant, but the person who committed the crime. If the person who committed the crime, if the probability that a male given carrying bottle is very high, let's suppose 0.9, then there is a high probability that it is the defendant who committed that crime. High probability because he's a male and who was carrying a bottle. All right. So this is what you have to evaluate: the probability that the person is a male given he was carrying a bottle. So let's try to evaluate that. The first thing that you might think is this M intersection B over probability of B. But where is M intersection B? If you misunderstood that, then what's going to happen? You would have put 0.02 here, which would be wrong. So this is why I ask you to always translate your questions well into probability notation. Do not just write down things lightly. Okay, write down into some probability notation. So you see that the intersection, the conditional probability formula doesn't apply here. So then what do you have left? You have the total probability theorem. The total probability theorem states that the probability of M given B is equal to the probability of B given M times the probability of M divided by the probability of B given M times the probability of M. So remember the formula, BK given A. So BK is M here and A is B. So what is happening? A is B, BK is M. Of course, BK B1 is M. B2 is what then? B2 is not M in this particular context. It's not M, which is F. So here we go. It is probability of B given M times probability of M plus probability of B given F times the probability of F. So I'll try to write this down. Where would I write it down? So let's have a look. I write it down there. Probability of B given M. This is why you see how easy it becomes when you have translated the information easily. You will see that this now I can answer. But the previous one, when B intersection M, I would not be able to answer it because I don't have this information. But right now, I get the information directly, which is 0.02 multiplied by probability of M, which is 0.6, divided by the same thing, plus probability of B given F, which is 0.01, times the probability of F, which is 0.4. You can evaluate that. If I'm not mistaken, you get 0.75. And when you get 0.75, it is a high probability. So you can say that there is a high probability that the defendant has committed the crime because it is relatively high, this value. Okay, you can say that there is a high probability that the defendant has committed the crime, since there is strong evidence. Since the probability of is high, there is strong evidence against the defendant. This is to answer your question. Do not leave your answer with 0.75, please. Do not leave your answer with 0.75, but answer the question. The question was, is there strong evidence? Yes, there is strong evidence against the defendant. So that's a little bit all in terms of Bayes theorem, but I just remembering a few things that I want to share with you. So that's all for Bayes theorem, but just to tell you something, if you have the probability of A given B, all right, you should not think that, for example, A given B is equal to the probability of A, sorry, you should not think that this is equal to 1 minus probability of A given B dash. This is not the case. Probability of A given B is not equal to the probability of A given B dash. That does not make sense. Right? Be careful with these things because B is a particular sample space. You cannot take 1 minus probability of A from a different sample space. If you are A given B and you say 1 minus probability of A dash given B, then this is okay. This makes sense. Probability of A given B is equal to 1 minus probability of A dash given B because you are talking about the same sample space, so you have the right to subtract. This is not a problem. The other thing that I said to you earlier, I think I already mentioned that, probability of A and B is equal to the probability of B and A, right? These are the same thing. The other thing that you need also to remember is the probability of B given A is not equal to the probability of A given B, because remember again there are two different sample space. So that's a few things that I just wanted to share with you because I'm just getting this right now in my mind, so I just wanted to share that with you so that you don't get this wrong. Okay, so thank you for your attention. You please do all the activities that are left, and then we shall discuss them in the tutorial time. Bye.